So you're going to title this exponents. And this thing called exponential decay. Decay means like when things decrease, when they go down. Last time we were looking at what happens when things go up exponentially. Now we're going to be looking at what happens when things go down exponentially. Okay, so we're going to look at some examples, then we're going to draw a graph of it there too. So I started to draw in our coordinate grid for our graph. Okay, so places you see exponential decay. Medicine. A lot of times medicine will decrease after you've taken it. Anything that bounces, so like a bouncing ball. And like I'm thinking a tennis ball. When you drop a tennis ball and it bounces and it slowly starts to decrease every time. Same with basketballs, soccer a little bit too, soccer balls, but that might be a little bit different. You might be on grass. There's this other thing too. Maybe you've heard about it. It's a science term. It's called half-life. And by half-life, we mean like some sort of decay as something decreases. So half-life is a science term that relates to something decaying, something going away. So these are all places that you're going to see exponential decay. And the graph of it, of the medicine, of the bouncing ball, the half-life, they all look kind of the same. If we were going to graph the height of a ball after you bounce it, it's going to look kind of like this. You have a beginning value up here somewhere. That might be like your release value of a tennis ball. And then after the first bounce, you might end up like down here. And then after the other, you end up over here. And the height's slowly decreasing, kind of like that. So exponential decay kind of goes down kind of quickly, but then it curves. The rate that it's going down starts to slow down. That's called exponential decay. All the graphs will look like that. Maybe it might be a little bit steeper at the beginning. Maybe the curve might be a little bit more dramatic, but they all look kind of like that. They curve down. Who uses this? Let's say uses. So we see it with medicine, bouncing balls, half-life. The people that use this in their careers all the time are doctors. Doctors have to often consider exponential decay with medicine. Scientists, whether they're running experiments or they're designing new things, they're working with exponential decay. Actually, I heard on the radio today, some of the coronavirus scientists, they're working with exponential decay right now, trying to figure out how effective the vaccine is going to be and for how long. Engineers, all kinds of engineers, computer engineers, civil engineers, mechanical engineers. A lot of times physics has things that decay exponentially. And so many different engineers use it in their work. And the way we keep track of exponential decay is kind of like with exponential growth. We use this thing called a standard function. The standard function. And the standard function looks like this. Y equals a parentheses b to the power of x. It's actually the same function that we use in decay or in growth. Growth and decay use the same equation, which is pretty cool. But the way that they act differently has to do with this B value. For something to decrease, you need to have a B value that's in between 0 and 1. So we'd write it like this. So basically we're talking about like a fraction or a decimal. If it's not in between 0 and 1, like if it's above 1, then you get something growing. Like what we were looking at, if B was like 2 or 3 or 4, that's your growth rate. But if B is a decimal in between 0 and 1, then like let's take the example of 1/2. If the growth rate was 1/2, well, then you're not growing anymore, you're actually decreasing. You're growing by 1/2, so you're going down every time. So the standard function looks the exact same as before, but our B has to be between 0 and 1. The A is still a start value. The B, I'm trying to remember what it's called. I don't think we call it a growth factor. We'll call it a decay factor. I'm not sure if that's right though. In our investigation today, we'll come across that. We'll change it if we need to. Okay. So is there anything else before we get into our investigation? We have our function. We know that it creates a graph like this. We can use a table, right? Just like with growth, you can use a table to track decay. You would expect things to the numbers to go down as you proceed. Oh, here's something that might be useful. And actually, we never talked about this with the growth, but it works in the growth too, is ways to find B. How to find B. Because you're not always told what the growth factor is or what the decay factor is. The way you can find B is if you take where you are now and you divide it by where you were before. So I might even say to find B, you go now divided from before. So like if you were tracking coronavirus, like in our homework, well, how many infections do you have now? How many did you have before? If you divide those numbers, you find your growth factor. Where are you at now? Where were you before? Same with the tennis ball. If you drop it, where were you at now? And then where were you before? And you should see that it went down. I think that's everything. Okay, I want to share with you a couple videos to get us into our investigation. We're going to learn more about where you use exponential decay, but then we're also going to practice more with actually calculating it and using like the function, using some numbers. So if you have a calculator today, that'll be useful. Start on it together here. It's going to look like this. It says when a large spill of a contaminant like oil happens in a large body of water, we use boats called skimmers. They mentioned that in the video. Skimmers filter the oil out of the water. The way it works is they put a hose into the water that sucks up lots of water continually, and the water goes through a big filtration system on the boat, and then clean water comes out, and so they put the clean water back into the water. The oil that's removed is then dumped into another boat that takes it away. That is their process for getting rid of the oil. So imagine there was a large oil spill in Puget Sound, and we sent a skimmer to the spill, and it starts filtering out the water. Because of the size, the spill of the boat will likely spend over a week. Which day do you think most of the oil would be filtered out? Go ahead and take a guess right there. Anyone want to share with us, what do they think? When do you think the oil, what day would mostly be filtered out? The second day? Okay, sure. I'll put that in here, and you guys can put in whatever you want, whatever you think. Do you think the amount filtered out each day would increase or decrease as the weeks go on? Do you think they're going to be filtering out the same amount every day, or do you think it's the amount they take out is going to increase or decrease? Wouldn't it probably decrease? Like, once you take like a lot of oil out at once, and then it might kind of slow down a little bit because you already took a bunch of oil out, and then maybe it kind of is spread out, so you have to go find some more. I'm thinking it might decrease as the week progresses. In the end, do you think they're going to get all the oil filtered out? No. And they even said in the video there that there was a big disaster, oil rig that caught fire about a decade ago, 10 years ago, and they still don't have all the oil out. They think they don't have all the oil out. They think it's hurting the animals. So thinking about the above questions, which do you think would best represent the amount of oil remaining in the sound each day? So X is time and Y is amount of oil. So as we take it out, does it look like this? Does the amount of oil just decrease constantly? Or does it look like B, where the amount of oil you take out is a lot and then it slowly decreases? The answer would be B. That's an exponential decay graph. The amount you take out every day, the amount of oil you take out every day is going to be less and less and less and less and less. Okay, slide 2. The data for the amount of oil remaining in the day is given below. Study the table. We need to find out the decay factor. Oh, I was right. It is called the decay factor. Good. I couldn't remember that. So in other words, what factor is multiplied to get from one day's remaining gallons to the next? You could answer this with division, but we don't because in the standard function, there's multiplication. So look at that table. How do they go from 2,400 to 1,200 to 600 to 300? What are they multiplying by each time? If you're not sure, then what you do is you take where you are now, like maybe 1,200, and divide it by what came before, 2,400. So if you divide 1,200 by 2,400, you get 1/2. So what we would say is the decay factor is 1/2, or you could go 0.5. It doesn't matter if you want to use decimals or fractions, totally up to you, doesn't make a difference. You should always have something between 0 and 1 though, if something's decaying. So we're not going to say you divide by 2, instead we say you multiply by 1/2. So let's see how many would be, let's see, calculate the remaining values in the table. So 37.5, and we have to multiply it by 0.5 or by 1/2. 37.5 times 1/2 is 18.75. And then that times 1/2, 9.375. 9.375. My table doesn't want to fit. Well, there we go. Okay. So to get to the 12th day, we just keep going. And I take what I had before my calculator and I go times 0.5. So there's 9, 10, 11, 12. So it looks like we're gonna have to round. It's 0.5859, so about 0.59 gallons. So you're dividing the number by half, or multiplying it by half, by half, by half. So half of a half of a half over and over again. With the exponential growth, we had A and B in our equations. So here's what our algebraic equation would look like here. Y equals our start value. Let's see, we started with 2,400 gallons. So 2,400, and then parentheses, this is your decay factor. I'm using a decimal, so I'm gonna put 0.5. And then the X is still left up in the exponent. If you put that into your calculator, you could use your table, you could use the graph. Okay, let's try another one. And so you see now why they won't get all the oil up. If you're taking a half every day and that's what you're collecting, then there's always going to be like a little bit left. Eventually it'll get really, really tiny. There's always a little bit of oil left. So the following represents the height of a ball bouncing on consecutive bounces. It was dropped from 243 feet in the air. We're getting into some decimal numbers. Okay, so what is the decay factor in this problem? In other words, what are we multiplying by to get from one height to the next? So it's not 0.5 anymore. The way you figure it out is you take where you are now divided by where you were before. So we could work anywhere on the table. I'll start at the beginning, kind of over at the front. If we go 140.94, if that's where we are now in stage or bounce number 1, if you divide it by where you were before, 243, that'll give us our decay factor. So let's see, what is that? 140.94 divided by 243, 0.58. Okay, so that's one tricky thing with growth factor and decay factor is actually figuring that number out. The last time you were given the number every time. Now we weren't given it, we had to calculate it. And with that, we can finish the table here. 47.41, how many twos is there? 2, it's like 2216 times 0.58. So this would be about 27, I'm gonna round, about 27.5. If you want, you can have your calculator put those in tables for you today. If you have a graphing calculator, if you don't have a graphing calculator, then you would just do the multiplication by hand. And we need our algebraic equation. So it always starts with y equals our start value, in this case, the height in feet on bounce number 0, like our release height, 243, parentheses, the decay factor we found, 0.58. And up to the power of x. X is going to be like the stage number again, like it was last time, or the bounce number, or the day number. And then y is whatever it is you're measuring, the height, the gallons. On what bounce, let's see, type your equation and check your values. Sure, we can do that. Just like before. On your calculator, you're going, let me show this again. For those of us using graphing calculators. You're going to go y equals, so maybe you're on the screen here. You go y equals up here. Our start value, what was it, 243? Parentheses, 0.58. It was 243, right? Is that our start value? Yeah, okay. To the power of x. And then we're not going to use the graphs. Instead, we're using the table like before. So I go second, graph, and there's my table. It should match. And so it was asking, when is the bounce height going to be less than 2? Well, it looks like right there, stage 9. Stage 8, the bounce was 3, just over 3. So stage 9 will give us what we need. What bounce the bounce less than 2 feet? Stage 9. Or I guess it's not stage, bounce 9. Okay. For the following equations, you're going to decide what their equation represents and then type in the answer. So this one, it looks like what we were doing before. What is that? An exponent of 10. So it's asking what's the height for bounce 10. And you can either type that into a calculator and see what the value is, or just look at your table. It would be 1.0 0.0469. I think it was measuring in feet. Is it feet? Yeah, feet. This one, same kind of thing. What's the height for bounce 19? One thing that's kind of interesting is eventually the ball does stop bouncing. But eventually the ball is going to just be on the ground. But in these exponential decay problems, they never actually reach 0. You're always multiplying by 0.58. They just eventually the number gets so small that it's the same as 0. Like on balance 19, you get 0.01 if you round. So that's very little bounce. Sometimes these inequality ones on the last one can be tricky. It's saying when is 1, the output 1, when is that smaller than your equation? Or the other way to think about it is when is your expression more than 1? So when are we bouncing more than 1 foot? When does the ball bounce more than 1 foot? And if you go back in your table, it's always above 1 foot until stage 11 is the first time that it's less than a foot. So we would say everything before bounce 11. That's a lot of bounces. 10 bounces and you're still a foot high. But I mean, it makes sense. We dropped it 243 feet. It's like dropping it off like off a building. So they're saying it's going to bounce about 11 times, 10 times. Okay, I'm going to do one more with you, and then I'll release you to work at your own pace. On the next one, here's a way like doctors might use this. Maybe you'll be a doctor in the future and you'll use this too. An important concept with exponential decay is something we call half-life. You might have heard this before. There's a game out there called Half-Life, but it comes from the science term. Half-life is defined as, and this is important, it's how much time does it take for half the original amount to remain? How much time does it take for half of the bounce height to still be there, or half the oil to still be there? They use this a lot when you discuss radioactive material, and also when you talk about the body absorbing medicine. For instance, have you heard of the drug insulin before? Maybe you know someone who uses insulin. So the body actually creates insulin, so we all have it. It's needed by the body to maintain your health. However, if someone has diabetes, they have trouble with the amount of insulin in their body. Therefore, if some diabetics have to take insulin shots to assist their body, and insulin breaks down pretty quickly inside your body, and the rate varies depending on the individual. But the following table shows a typical pattern of the amount of insulin in the body as time passes. So look at the graph. What appears to be the half-life for insulin? So it's saying, when does it appear that half of the insulin's gone? Your body's used it. So you have to look at the y-axis. We start at 10. And then half of it would be right around here, around 5. So it looks like we're on the decay graph right there. And so then if we go down here at the x-axis, I think that's about 15, right? So we would say the half-life is 15 minutes. Oh, wow, this is not aligned to my table at all. I need to space over. So it's about 15 minutes. In 15 minutes, half the insulin from an insulin shot's already gone, or half the insulin your body produces already gone. The pattern of decay shown on the graph is that equation there. What do you think the 10 and the 0.95 means? What does the 10 mean? Do you know what the 10 is? We'd say it's the initial value. I'm gonna get rid of my table, that thing there. There we go. So 10 is the initial value. What does it say? It says the amount of insulin in the bloodstream. Oh, they didn't label it. It might be like milligrams or something. So it's like the amount you initially took in. And then 0.95 is the decay value, or decay factor. To the nearest 10th of a minute, what is the half-life of insulin in this situation? So this is where it gets a little bit tricky, and I'll need to show you on your graphing calculator, for those of you who have it, how you can get to the nearest 10th. Okay, so let's go back to the calculator here. The first thing we need to do is we need to type in our equation. So we're using y equals 10 parentheses 0.95 to the power of x. And I delete everything else. I don't want anything else in there. Now, if I just go to my table, it's going to go by ones the whole time. 7, 8, 9, 10. However, let's see. I have to remember real quick. Where does it come up? Yeah, there it is. Okay, so you're on your table. What you're going to do is you want to go to this this button here. It's kind of the second one over where it says window. Up above it says table SCT. The way I remember this is like your table settings. So if you press second and then press window, it'll go to the table settings, and then you can change where you want it to start. And then this little triangle TBL, remember the triangle in math means change. So this is saying how much do you want your table to change by? It's always going to go by 1, unless you go down here, you can tell it to go by 0.1. And then everything else you just leave the way it is. But by changing that to 0.1, now if I go back to my table, my x's are going to go 7, 7.1, 7.2. And so we can go down and find out if the half-life is actually 15. Let's look. There's 9s, 10s. You know what? Instead of going down all the way, I'm just going to tell my table to start at maybe 14. And then that's going to save me some scrolling. Oh, see, at 14, we're actually past the half-life. We're looking for a value, y value of 5. So the half-life actually is right around here, 13.5, 13.6. So I don't want to go to 13.6 because we're already past the half-life. Instead, I go to 13.5. Okay, so if you don't have a graphing calculator today, you might have to skip those questions or find another way to calculate it. But if you do have a calculator, then it's really nice because you can just tell it to go by 0.1, and then it'll get you to the nearest 10th. So according to the graph, it looks like the half-life is about 15 minutes. But actually, we find out from the equation that the half-life, well, I don't know why any of these aren't lined up very well today. The half-life is, what was it, 13.5. That's the time when half of the insulin's already gone. Okay, so we did a lot together today. You're gonna go on to slide 5. It's gonna ask you more questions about insulin. And then on slide 6, there's only a few questions. It's gonna ask you about penicillin. And then number 5 is gonna ask you about Benadryl. And then 6 is gonna tell you about some x-rays